Hello, everybody. My name is Pawel Biernacki, and I'm going to talk today about a new algorithm, artificial intelligence algorithm, which is Perkun. The first slide, I have 17 slides. I thought about 15 minutes and then about the questions that you might possibly want to ask. What is the difference between a Perkun optimizer and traditional if-then construct known from multiple programming languages? First of all, if-then is stateless. It doesn't have any state, it doesn't have memory, it doesn't remember even its own actions, and it ignores history, therefore. So you might think about a human being or even any intelligent being as a function mapping input to output, but this is a naive approach. This is something that we want to make a little better. A Perkun optimizer is like from the object-oriented programming. It has a state. It is an attribute called belief, and this belief is updated repeatedly. I will show you an example of a belief. I have a slide for that. And there's also a certain rationale behind Perkun that it attempts to maximize so-called payoff function, expected value of a payoff function. Payoff is something that defines how good your input is. I have a slide for payoffs also. I'll show you them. And it builds a game tree. It is therefore somewhat similar to Minimax algorithm, but we don't have an opponent here. We just act as a standalone player. And the second difference is that we don't see everything that is happening in the game. And third, we perform the actions one by one repeatedly. So I have also a slide for game tree. Next slide. Hidden variables. This is the heart of my new algorithm. They are introduced to generate beliefs. So you obviously can't imagine that, if you're not a solipsist, of course, that we perceive all the variables, and it's quite easy to prove that introducing hidden variables makes it easier to predict future. I don't have a proof here, but it is really simple. The hidden variables are introduced to generate belief, and they have as a domain a collection of states. It is so that for every visible state we may have a belief, and a visible state is a vector of input variable values. So just the values of what you can see. And for each such visible state, there is a collection of substates inside that specify hidden variable values. I have also a belief. I will show you how it looks. But the most important thing from this slide is that we have the hidden variables introduced. They act just like normal variables, but we don't observe them. We don't perceive them. Now I have two slides that specify what Perkun needs to know and what Perkun can do for you. What Perkun needs to know, it is reflected by its specification. It is the values, the constants that are used to define variables. Second, the variables, input, output, and hidden variables. Usually I use only one output variable, but this is something you can change. The input variables, I think it's obvious, and hidden variables are the variables that we introduced on the previous slide. The payoff function, it tells you what combinations of what values are beneficial for you, for the agent, and what values are bad. What is good, what is bad for you. The payoff is a function in a mathematical sense. So for each combination of the input variable values, we have a value. It is a real number, a positive number. I don't support unary minus, I think. And the model. Model is something that tells you how the world works. and it is not limited only to the input variables. It is telling you, it is like the rules in chess, for example, chess game. Game tree height is something that tells you how deeply we go into the game tree. So this is all we need to know. The skeleton are the variables. They are the most important. Now, what Perkun can do for you once this knowledge is provided? It can predict result probability. So for each visible state, it may predict how likely it is, given current belief, how likely it is that after one action we will perceive this result. Calculate result interpretation. So a new belief. I told you about the state of a Perkun optimizer, which is a belief. And these two things are hidden, so they are not directly perceived when you work with Perkun. And find optimal decisions. This is the most important functionality. So the decisions are optimal. I don't have, unfortunately, any proof for this algorithm, so that these decisions are really optimal, but it works. I will show you later. Okay, now I'd like to talk about a simple game, PerkunWars, that you can download. It is downloadable. It is implemented in C++. Not a good game, but a very good example how to use Perkun. You're hunting a vampire. There are 3 locations, and they are called Vizima, Shadizar, and Novigrad. And you have the NPCs around. They can be in either of the 3 places, and the vampire can also be there somewhere. You don't know where the vampire is unless you can see him. When you see him, you know he is in your place. And it is really a simple game. It is just so that it is useful to attack the vampire when the NPCs are around, because they are going to help you. But not all NPCs are the same. One of them is a Witcher, so he's repeatedly trying to catch vampire, and 2 others are normal humans. They are avoiding vampire. Okay, so this game is something you can download and take a look, especially take a look at the source code. It is working on pipes and processes, and for each NPC there's a process that runs Perkun interpreter, because Perkun is an interpreter. I should have told you that in the beginning. It is an interpreted language. But you don't need the game to run Perkun session. When you download the Perkun 0.1.7 targ gz file, you can unpack it, and in the examples folder, you'll have multiple files, including example 3 Pregor and example 2 Dorban. Pregor and Dorban are the NPCs from the game. So you don't have to download the game, and you can, once you install, build and install Perkun, you can do something like Perkun example 2 Dorban Perkun, and then you enter Perkun session. In this session, you are free to enter the values of the input variables, and after that you receive a belief and the optimal action chosen. So let's talk about the second example, example Dorban. Dorban is a Witcher, so when I input place Vizima false, it means you are in Vizima, you don't see vampire. He will think, aha, then the vampire must be in Shadizar or in Novigrad. Let's go to Shadizar. The algorithm is deterministic, so I know for sure that he will decide to go to Shadizar. Then I will say, place Shadizar false. He will say, okay, the vampire must be in Novigrad then. And this is confirmed when we enter Novigrad. Now, this is the algorithm from the top level view. It is 4 steps, And the third step contains building a game tree. I have a separate slide for game tree. So first we have get input. If you use libperkun, which is a library based on Perkun, then in this get input you have a memory structure, a data structure that should be filled with the variables. It is a mapping, std map. You probably know it from C++. So this map is filled with values of variables, of input variables. Then we have interpretation. It is something given the former belief and former action and current input. We are predicting how we will interpret this input. So what we are going to believe now. It is this probability distribution over the states, over a collection of states. Then we get optimal action, and this is where we produce the game tree as deeply as we want. So it should be 1, 2, 3, some constant pass to the Perkun interpreter, and then we execute the action. This is the algorithm from the top level. Now I will talk about the game tree. It is somewhat similar, as I told you, to Minimax, but in the Minimax we have opponent, and here we don't have opponent. Second, in Minimax, the consequences of our actions are deterministic. I think it is like that in chess, for example, or in checkers. I'm not sure. I think in multiple games you could use Minimax also when it is not deterministic. In Perkun, anyway, it is not deterministic. So we have transition probabilities, so-called transition probabilities. And we have, in the top level, we are taking argmax from the actions. So there are 4 possible actions. Go to Vizima, go to Novigrad, go to Shadizar, and do nothing. And then after each action, we have possible visible states. For example, when we go to Vizima, we can have place Vizima true or place Vizima false. And we imagine how do we interpret what we're going to believe once we get to Vizima and we don't see vampire. If we don't see vampire, for example, and we just started, then we will think that the vampire is in Novigrad or in Shadizar. But if we have been to Shadizar just before, then we will know that the vampire is in Novigrad. If I didn't make a mistake, then you know what I mean. So this is a game tree. There are 3 command line tools in the Perkun package and 2 libraries, Perkun, Włodkowic, and Żubr. The name come all from Polish. I'm sorry, that might be difficult. Włodkowic is something like Perkun. It is also an interpreter, and there's a library for Włodkowic. It differs only so far that we have a priori, so the prior probability as a separate section, while in Perkun we assume the uniform probability, which is also a simplification. So when we don't see vampire somewhere, say in Vizima, we will know 50% for Novigrad, 50% for Shadizar. But it doesn't have to be 50% in the nature. For example, if you have a patient who's coming to you and you have a medical system, then you might say, okay, he may have a cancer for 5% because this is a natural distribution. I don't know whether it's 5%, but I assume it's somewhat less than 95% that he doesn't have cancer. So this is an extension in Włodkowic. Also, there's another thing in Włodkowic, but this is basically the same thing as Perkun. And Żubr is something that you can use to generate. It is like Bison, if you know the parser generator, but it doesn't generate a parser. It generates an optimizer, a class, and it is not generating anything in C, but in Java. But I will not talk about Zubr anymore. Perkun specification. This is how it looks. So if you take a look at this folder, examples, at the files with Perkun, this is a strict form language. So first we declare the values which have been omitted here, then the variables, and this is the most important. After each input, output, hidden variable, we have the variable name and the list of possible values. So for example, there's input variable, where is Dorban? This is taken from the Dorban specification. Dorban is this NPC who is hunting the vampire. And he may be in one of the three places. Place Vizima, place Hadizar, place Novigrad. And input variable, do I see vampire? False, true. So we have 6 possible input combinations. There's one output variable, and there's a hidden variable, where is vampire? And this where is vampire is not directly perceived. Of course, when you see the vampire, you know that he is there. But if you don't see him, then you're not sure where he can be. It depends on the past, on the history. And therefore the belief is important. Then we have in the Perkun specification the payoff function, model. Model tells you how the world works, and any number of commands. I have only one command here, which is loop, with the game tree depth as a parameter. You can't use any expression. I'm sorry about that. You have to use 1, 2, 3, a constant. So this is a Perkun specification. And if you take a look at the game, at the PerkunWars, you will see that this Perkun specification is produced in a very special way. There's some prologue involved there, but it's just to produce a specification. And Perl. A belief. This is an example of a belief. It is a belief that we have when we are Dorban and we enter Vizima and we don't see vampire. So you can see that there are 3 substates here. I call them states in the source code. And the first variable is the hidden variable, where is vampire? And the 2 other variables are input variables, and they don't change. And there's, for each of the states, there is a value, a probability value. So this is a belief, a probability distribution, a Bayesian probability over a visible state. And you can see that we don't believe the vampire is in Vizima because we don't see him here. We believe 50% that he is in Shadizar, 50% he is in Novigrad. Okay, that's all. And I use this image that you can see here in general for the belief. So it is a mapping. The optimal action, a very simple slide. So the values of the action can be one of the 4 values of the output variable. If you have multiple output variables, then this is more interesting. You might have parameters, for example, for the output action. Now, this is an interesting slide. It shows you the difference between payoffs. Payoff is filled with the instructions called set. And the set instructions, on the left side you have the Pregor payoff. On the right side you have the Dorban payoff. You can see that they are taken directly from the specification, so I don't try to fool you. It's really something that works. When you have 100 on the Pregor side, you have 0 on the Dorban side, and other way around. When you have 0 on Pregor side, you have 100 on Dorban side, which works so that Dorban thinks that not seeing vampire, Pregor thinks that not seeing vampire is good. It is 100 points, while seeing vampire is bad. It is when you have do I see vampire true, then it is 0, and that's why it tries to avoid vampire. whenever you enter a town where the vampire is, and you can see him, then he will try to move to a different place in the hope of not seeing him anymore. While Dorban is exactly opposite. So he has 0 for not seeing vampire and 100 for seeing him. Model. I have a separate slide for model here. In the model, you have also set instructions, and they are the most important. They define the transition probabilities. You can also take a look. Models are difficult to build, but it's not any difficulty like conceptual. It is something that has to do with the size, because they are usually very large. Apart from that, apart from the transition probabilities, which are obligatory, you have illegal actions and impossible states. Illegal actions, so for example, when you are in Vizima, you can't use go to Vizima. This action is illegal, so you define it with an illegal instruction in the model. And impossible states, also an example, when you see a vampire, but he's not in Vizima, but you are in Vizima. This is impossible. So you have to also define that this state is impossible. And therefore, in the belief, you will have 0 probability for this state. Now, the interesting achievement of this algorithm. This is almost the last slide. When you have a game tree depth greater than 1, and you have some experiments, when you have actions with neutral payoff, for example, do nothing gives you 50, and ask a question, perform some experiment, gives you 50 also. But the later one is differentiating the beliefs. And you have some way to use the action you have gathered. Then, depending on the belief, the algorithm will make decision to ask questions, and this is something I consider very cool about it. So you can sometimes see that Perkun is performing actions that allow him to gather information, but only when you have this game tree depth greater than 1, and when the other conditions here are fulfilled. Okay, now the links follow. The links, you can take them from there, and also my business card is there. And if you have any questions, I can try to answer. Thank you.